This is part 2 of lecture 9 of Kardinalna aritmetika, and as you have already been told, this is an optional part lecture, and in it we're going to prove the very strange Banach-Tarski theorem. And as I've mentioned before, this proof is not examinable, so this is purely for your own interest. So let me remind you what the Banach-Tarski theorem says, and it really is a strange theorem. So it says that the unit ball in three-dimensional space, so that's the closed ball of radius 1, can be partitioned into a finite number of pieces, so that half of those pieces, the A pieces, can be collected together, and each one of them subjected to a proper rigid transformation. That's a combination of a translation and a rotation. And in doing that to each one of these finite number of A pieces, we reassemble those pieces into another copy of the unit ball. So we've taken just a part of the unit ball and reassembled it into the whole of the unit ball. And the B pieces we can do exactly the same with. So from that we're getting we're splitting the unit ball into 2, and from each part getting back a whole unit ball back. So from 1 unit ball, in the end we get 2 unit balls back. Sorry, here's the bit where we get the balls back, because we've subjected the A's to some proper rigid transformations, and we get the ball back, and we've subjected the B's to some proper rigid transformations, and again we get the ball back. Okay, so we're going to look at the proof of this. It's going to take quite a lot of steps, and the first part is really quite abstract, and it requires a little bit of knowledge of group theory and group action. So I'm not going to be able to give you the background in this lecture. So, hopefully many of you will know enough of the background to be able to understand what's going on. So I'm going to identify 2 particular points from the statement of the Banach-Tarski theorem. So two important aspects. Of the, let's just call it the BT theorem, because I'm going to write this a few times. Don't want to write it out in full every time. So 2 important aspects of the Banach-Tarski theorem are we're looking at a subset of 3-dimensional space, namely B, which is the closed unit ball, and we're partitioning that into a finite number of pieces. So we're looking at a finite partition of a subset of 3-dimensional space. So it concerns finite partitions Remember, a partition is just dividing a set into a number of disjoint pieces, subsets. So it contains finite partitions of a subset of 3-dimensional space, R cubed. And with that finite partition, what we do is we subject individual sets in the partition to proper rigid transformations. So we're using these proper rigid transformations, which are combinations of rotations and translations. And there's a group of such proper rigid transformations. It's called SE3. That's the usual terminology for the group. And we can translate a subset of any subset of three-dimensional space. We can subject to a proper rigid transformation because the group of proper rigid transformations acts on the set, acts on three-dimensional space. So it concerns the behavior of such partitions under a group action. Under the action of a group. So it's a particular group. So as I said, it's called SE3 normally, and this is the group of proper rigid transformations of let's say, on three-dimensional space. And it doesn't matter if you haven't met the group SE3 before, because as I've already told you a couple of times, a proper rigid transformation is just a transformation that is a combination of rotations and translations. So these are two important aspects, and we're going to begin by actually considering this idea of partitioning subsets, partitioning a subset of some space and subjecting the partition to the action of a group. We're just going to look at this at a much more general than this particular group on three-dimensional space, and that's just at the level of generality of an arbitrary group action. So an arbitrary group acting on a set. So it is useful to consider these aspects at the at the greater level of generality of arbitrary group actions. So accordingly, we're going to assume we have a group action to work with. So accordingly, let G be any group acting on a set X. And just to remind you, this means that for any element little g of the group, we have a function that amounts to transforming the set X from, so we have a function from X to itself, which one can understand as translating an element, translating the elements of X according to the element of the group that we're given. So a group action. So this gives us an action function we we have an element of the group, and given an element of the group and an element of X, we get back an element of X, which one understands as kind of, as I said, translating the element of X according to the element of the group. So I'm hoping that you are familiar with the notion of group action. So the first step we look at the notion. We're going to introduce a notion of what we're going to call G equidecomposability. It's quite a long word, and it's composability. Hope I don't need to write it too many times. It's quite a long word, and it's a slightly complicated concept, but we will immediately recognize it as one that's very relevant to the Banach-Tarski theorem. So we've got our group G acting on the set X, and subsets A and B of the set that we're acting on are said to be G equidecomposable if they can be partitioned as, so we're partitioning A into n subsets, and whenever we say partition, that means the unions are disjoint. So here I'm writing it, but I don't need to write it really, so that's why I'm putting it in brackets. So we're partitioning A and B into a finite number of sets, the same number in each case, in such a way that the sets, each of the sets AI can be shifted to a set BI by applying the group action for some element of the group. So in such a way that there exist corresponding elements of the group, so little g1 through to little gn in the group G, such that we get B1 by shifting A1 using G1, and similarly for all the others. So all the way through till we get Bn by shifting An using little gn. Okay, so that's the notion of equidecomposability. Let's immediately relate it back to the Banach-Tarski theorem. So we immediately have, with this notion, a restatement of the BT theorem. So it now becomes a much shorter theorem to state because we've done a lot of the work in this notion of G equidecomposability. So the closed unit ball this should be bold B, blackboard bold B, can be partitioned into two. I'm just going to put A union B, where here A is the union of all the A pieces we had before, and B is the union of all the B pieces we had before, where let's say such that A is equidecomposable with the unit ball under the group SE3 of rigid transformations, and B is also equidecomposable under SE3 with the unit ball. Let's just check that that corresponds to the original theorem, but as we go back, I should here introduce the notation which I meant to put in. So let's put this here. So if A and B are G equidecomposable, then we write A is twiddle equivalent under the group G to B. That's our notation for that notion. Right, so here we're saying the closed unit ball can be divided into two pieces such that A can be divided into a finite number of pieces that can be shifted under proper rigid transformations to form to give a partition of the whole ball, and B can also be divided into perhaps a different number of pieces, but again a finite number of pieces that can also be shifted to form a partition of the whole ball B. And that is exactly what the Banach-Tarski theorem, the statement of it here, said. A is divided into some finite number of pieces, B is divided into some other finite number of pieces, and each of those can be shifted along the proper rigid transformations so that they can be reassembled to give a partition of the whole ball B. Okay? So indeed this notion of G equidecomposability gives a nice restatement of the BT theorem. And so we're going to, well, for the moment, work with this restatement of the Banach-Tarski theorem. But in order to do that, we're going to want some tools for being able to reason about G equidecomposability. So there are going to be some important results here. And the propositions are firstly, the notion of G equidecomposability is an equivalence relation on the power set of X. And this is actually quite a fun thing to prove. So exercise, prove this. I mean, of course, the whole lecture, this whole part of the lecture is optional, so the exercise is very optional, but if you want to, try to prove this. And the interesting part is transitivity. Okay, so that's one nice property about G equidecomposability. But we're also going to be interested not just in equidecomposability, but also so that's an equivalence relation, but there's a corresponding preorder. That's like the version of a partial order that does not have the antisymmetry property. So it's just a reflexive and transitive relation. So there's an induced. So we're also going to be interested in so there is a related preordering on the power set of X, on all subsets of the set that the group is acting on. And for this we define one subset to be, we're going to use a curly less than or equals sub G. So one subset is less than equals to another if and only if there exists a subset of B such that A is equidecomposable with that subset. Or maybe I don't need those brackets. Maybe we'll put such that. So this is a little bit reminiscent of the notion of, well, somehow one can think of equidecomposability as somehow reminiscent of two sets having the same cardinality, and then in which case the corresponding notion here would be, so one can kind of, whenever you have an equivalence relation on subsets of a set, you can always define a partial order in this way, sorry, a preorder in this way. And if the equivalence relation were two subsets being in bijection, this preorder would be that A is in bijection with a subset of B, which is of course the same thing as there is an injective function from A to B. So here our equivalence relation is not there exists a bijective function between the subsets, but it's rather the two subsets are G equidecomposable. But nonetheless, having made the above analogy, perhaps it won't be too completely surprising that there is a theorem that says that if A is less than equal to B and B is less than equal to A, then they are then A and B are G equidecomposable. So it's an analogue of the Schroeder-Bernstein theorem. So the theorem is if A is G equidecomposable with a subset of B, and also B is G equidecomposable with a subset of A, then in fact A is G equidecomposable with B. So not only is this very similar to, in form, to the Schroeder-Bernstein theorem, the proof is almost the same. There are just a couple of little additional steps one needs to do. So because of that, this theorem in this form is called the Banach-Schroeder-Bernstein theorem. So I'm not going to give you the proof. I think it would be too much to expect you to do it as an exercise. You can look it up if you wish. You can try to do it as an exercise. But I'll just say that it's similar to the proof of the Schroeder-Bernstein theorem. Okay, so that's the end of step one. We've restated the Banach-Tarski theorem using the notion of equity composability for the group SE3 in this case. And we've seen that equity composability is a well-behaved notion. It's an equivalence relation, and also to show equity composability, it's actually enough to show that A is equity composable with some subset of B, and that B is equity composable with some subset of A. So then you get that the whole sets themselves are equity composable with each other. Quite a surprising result, except that it's not so surprising when one views it in context with the Schroeder-Bernstein theorem and realizes then that the proof is rather similar. So that's the end of step one, the notion of G equity composability. We're now going to look at another notion at the same level of generality of a group acting on a set. So step two is another notion, the notion of G paradoxical. Set. So let's again just start by giving the definition here. So a subset E of the set that the group is acting on, X, is said to be G paradoxical if there exist disjoint subsets of E. So A1, again, it's going to look a bit like the Banach-Tarski theorem. This time we're going to be explicit that we've got M disjoint sets, A sets, just like in the Banach-Tarski theorem, and N disjoint B sets, but they don't need to be the whole of E, they're just together, they need to be the union of all of them, but they all need to be subsets of E. And once again, we ask for associated elements of the group, which we're going to shift these sets using. So we're going to ask for G1 up to Gm and H1 up to Hn in the group, such that, and it's a bit like the Banach-Tarski theorem in that we've separated out some subsets of two collections of subsets, the A sets and the B sets, and if we shift them by the corresponding elements, then the union of the A sets gives us back the whole of E, and the union of the B sets gives us back the whole of B. So G1, A1, union GM, so shift AM by GM is E, and that's the same thing as H1 B1 HN BN. So it looks, again, rather similar to the Banach-Tarski theorem. It almost looks as though the Banach-Tarski theorem says that the unit ball is SE3 paradoxical. It looks like this notion is basically wrapping up the Banach-Tarski theorem in a kind of more explicit way, even than in a more direct way than the notion of G equidecomposability was, because this looks very, very close to the statement of the Banach-Tarski theorem. However, there are a couple of differences here, in that in the Banach-Tarski theorem, then the union of all the A's and B sets was the whole of the unit ball. Here we are not requiring that the union of all these sets is E, and also we are not requiring that these unions at the end are disjoint. So that's also not part of the requirements in the definition of paradoxicality. So let's just say NB, we do not require that the union of all the A's together with the union of all the B's let's maybe take that colon out. Or that the unions in the last line of the definition are disjoint. So these unions need not be disjoint. However, what we're going to find out now is that although we don't require those, we can, if we have G paradoxicality in this weaker form here, we also have it in the stronger form in which we do require the unions of the A's and the B's to together be E, and that the unions in the last line are disjoint. So we're going to, so one way of saying that is as follows. So let's make it a proposition. So E is G paradoxical if and only if it can be partitions so divided into two disjoint subsets, partitioned as E is the union of A and B's, where A is G decomposable with E, and so is B. So this statement exactly gives us these two missing points here, because the A G decomposable with E, so the A's are the unions of the AM, of the A1 to AM, the B is the union of the B1 to BN. They partition the whole of E, so we have this equality here, and the G decomposability gives us that these are in fact partitions of E, and so the unions are disjoint. So I'm not proving many of the propositions, but this one is an important proposition, and the proof is illuminating. So the right to left implication is obvious. Because this is a stronger property. It's the same as G decomposability with these two additional points in it. The left to right implication is the interesting one. So suppose E is G paradoxical. With A1 up to AM and B1 up to Bn, as in the definition of G paradoxicality. Okay, so G paradoxicality gives us such sets A1 through to AM and B1 through to Bn. So suppose E is G paradoxical and we have those sets. So the first thing we want to do is ensure that these unions are disjoint. And actually that's easy. It's enough to remove elements, sufficiently many elements from the sets, from the A sets and B sets where there's an overlap here. And then one still has disjoint subsets of E that replace the original A's and B's. So I'm not going to write that out in detail, but it's rather easy to check that. So by shrinking, so again removing elements, the A1, AM, B1, Bn, if necessary, or as necessary, we can achieve that the unions at the end are disjoint. So in fact, it's very easy to put that disjointness requirement into the definition of G paradoxicality. Just gives, if you do that, then there's one more thing you need to verify. So it's easy to achieve that these unions are disjoint. So I'm not going to strictly speaking, we started off with some A's and B's, and we might then get some A primes and B primes, still M A primes and N B primes, but I don't want to introduce the notational overload there, so I'm still going to work with A's and B's. But having done that, we want to get this, we've made the set smaller, but in the end we want to be able to partition the whole of E into two parts, each of which is G equidecomposable with E itself. But to do that, well, we're now going to use our Banach-Schroeder-Bernstein theorem that we mentioned before. So we have E is G equidecomposable now with A. And this is a subset because now we have a disjoint union here. So we've achieved an equidecomposition of E with A. And A is of course a subset of the set difference E minus B, because the B's and A's were all disjoint. And this is of course a subset of E. So this is where we write A for the set A1 union AM, and B for the set E1 union Bn. So because of this, A is equidecomposable with a subset of E minus B. So therefore, we have that E it's equidecomposable with a subset of E minus B. So that means it's less than in the pre-order. E is less than E minus B, but also E minus B is itself a subset of E, so it's trivially decomposable with equidecomposable with a subset of E. So trivially, it's in the E minus B is in the reverse pre-order relation with E as well. So by the Banach-Schroeder-Bernstein theorem, so whence we have that E is actually G equidecomposable with E minus B by the Banach-Schroeder-Bernstein theorem. So let's I think we can finish on this sheet of paper. So if we define A prime to be E minus B and B prime to be B, we already have that B here, this is a disjoint union, that B is equidecomposable with E, and we've now got that E minus B is equidecomposable with E as well. So give A prime is G equidecomposable with E is equidecomposable with B prime, and A prime union B prime equals E. But anyway, this give us the this A prime and B prime give us the partition that we require. So the A and B in the proposition are A prime and B prime that we have just defined. So as required. So given this, we now see that, as I said, the missing points from the Schroeder-Bernstein theorem have now been we've shown that G paradoxicality actually implies that we have those missing points. So by the proposition we have what I'm going to call the second restatement of the Banach-Tarski theorem. And this just says the closed unit ball B is SE3, the group of proper rigid transformations, paradoxical. And it is the second restatement of the Banach-Tarski theorem we prove. And we're going to do this in a sequence of steps by working our way towards proving that various sets under various groups are paradoxical, and eventually working our way towards the closed ball. So we're going to do this in a sequence of steps. And we're going to combine steps using a useful little lemma. Which we combine using so let's put the lemma in black, which is if we have a subset of the set the group is acting on and it's G paradoxical, and we have another subset that's equidecomposable with E, then E prime is also G paradoxical. So if we establish equidecomposability of two sets, we can transfer the paradoxicality from one set to another. And the proof of this is easy, so this can be an exercise too. If you once again a very, very optional exercise. Right, so but it's not difficult. Right, so maybe let's draw a line under, not a line in the middle of the sheet, but I was going to draw a line under it. Exercise, let's fix that. Let's draw a line under here, and we're going to move to the next step. But beforehand, let me just comment just a little bit on the notion of G-paradoxicality, because of course this is now crucial. This is what we're going to show. So the reason for identifying this notion of G-paradoxicality is it contains the essential elements that we can take our set E, we can find a partition of some parts of it and another partition of another part of it and reassemble those to get E back. But it doesn't have these two requirements here, and in particular the last one, that it doesn't require that all these things union together to make the whole of the set. That's very, very helpful because it's much easier to show that we can find some subsets that we can reassemble to make the whole thing than that we can neatly fit all the sets together to actually partition the whole of E in the first place. And instead, that last bit we're getting by a general result, which has quite a complicated proof, because although this part of the proof was easy, it relies on the Banach-Schroeder-Bernstein theorem, and as you will remember, the proof of the Schroeder-Bernstein theorem itself is quite complicated. Right, so the first group we're going to do, so we're now going to get to step 3. Oops. And we're going to show the paradoxicality. I don't know if that's really a word, but it sounds right to me. So let's say paradoxicality of the free group F2. So what is the free group F2? Well, F2 is the free non-abelian, so it's a non-commutative group, on two generators. So what that means is we're forming a group starting with two tokens or letters, let's call them little a and little b, that generate, so each of those is an element of the group, a and b is an element of the group, and we need to be able to multiply those things, all elements, in a way that doesn't need to be commutative because it's the free non-commutative group, non-abelian group, but of course it must still be a group, so you have to have inverses and they need to work properly. So the free group, it's easy to understand it, what it is, the free group on two elements. So every element of F2 can be written uniquely as a word. That's just a sequence of letters over the alphabet. Well, we're just giving ourselves two letters, namely the two generators of the group. But we also want each of those has an inverse, so let's actually give ourselves a letter for the inverse. So we'll just call the inverses, I could say letter, but it's going to be so a to the minus 1 and b to the minus 1, so we consider that as part of the alphabet. And these words that are reduced. The point is, so we're combining a and b and a to the minus 1 and b to the minus 1 by multiplying them together, but multiplying just means juxtaposing the words, that's writing them side by side. But if we do that, we don't ever want a b to appear next to a b minus 1 because they would cancel, because b times b to the minus 1 is, of course, the identity element. And also we don't want a to appear next to an a to the minus 1 for the same reason. So every element can be written uniquely as a word over the alphabet. That there's a grammar mistake there. There should be that is reduced. So the symbols a and a to the minus 1 are never adjacent to each other. And adjacent means next to. And the same for the symbols b and b to the minus 1. So we can then see that this group indeed contains, it is a group. These reduced words are we can view them as the elements of the group. The identity element is just the empty word. So we allow the empty sequence of symbols from the alphabet. So it's rather awkward to write the empty words. So in computer science, one uses theoretical computer science, one uses a kind of curly epsilon symbol for the empty word, because if you just write it without that, it's empty space, or you might put just two quotes next to each other or something like an empty string in a programming language. But anyway, the standard mathematical notation in computer science is this curly epsilon, so I'm going to use that. The group multiplication, so if we multiply two words, so if we multiply, let's use the dot for multiplication, word w and w prime, is by, we simply concatenate the two words. So we perform the catenation, so put the two words next to each other, followed by reduction. So reduction means changing it to making sure it's a reduced word. So for example, if the word W ended in A and the word W prime started with A to the minus 1, when we stick the words together, we're going to have A and A to the minus 1 next to each other, which we're not allowed in a reduced word. So we just remove those symbols, A and A to the minus 1. We then may end up having two new symbols that are inverses of each other next to each other, in which case we remove those, and we keep on removing such pairs until there are no more such pairs in the word to remove. That's the process of reduction, and that gives us how multiplication works on the group. And now our lemma is going to be, let's have it as a proposition rather. So proposition that the group F2 is itself paradoxical So remember, any group acts on itself as a left or right action. So here we're going to take left action. Doesn't really matter. Everyone doesn't need to be too fussy about this, but so let's just put that down. F2 acts on itself as left action. Don't worry too much about, these, if you're not very familiar with groups and group actions, these left and right things get, I know they can be confusing. Doesn't really matter because the paradoxicality is actually rather easy to see, in that what we're going to do is we notice that F2 can be written as a union where it's the empty word, together with what I'm going to call WA, which is, let's say what this is. This is the set of all reduced words starting with A, union W of A to the minus 1, union W of B, union W of C. Oh, not C. Where's C coming from? B to the minus 1 in this case. Now this equality is literally obvious because the group is all reduced words over the alphabet. A reduced word is either empty, in which case it's in this set, or it's non-empty, in which case it has a first letter, and that first letter is either A or A to the minus 1 or B to the minus 1. So every reduced word, that's every element of F2, falls into exactly one of these sets. So this is a disjoint union. This is disjoint union. And the notion of paradoxicality we want to find some subset. We've got a subset, we want to find subsets. So our subset E is F2 itself here. We want to find subsets A1 through to AM and B1 through to Bn that we can then shift them by using group elements and union them together to get the whole group back. And in this case, we're going to have this. These are the A sets, and these are the B sets. So we are starting with sets that the union of the sets is not the whole of the set we're dealing with, is not the whole of, so this is playing the role of E in the definition of paradoxicality F2, and these sets do not union to E. So we're really making use of the level of generality allowed by the definition of paradoxicality, that the sets do not need to union to E itself. And we notice that then we have that F2, we can get it by as WA union A of W of A to the minus 1. Because, once again, every word in F2 either begins, it's a reduced word, it either begins with A, in which case it's in WA, or it doesn't begin with A. So it might be empty, but the empty word is obtained as, so that's the identity element, that's obtained as A times A to the minus 1, so that's indeed in this set. Or it begins with A to the minus 1, in which case it's in, if we add another A to the minus 1 to the start of the word, then we can get the word as A times A to the minus 1 times the word beginning with A to the minus 1. Or if it begins with B, we can do a similar thing. So it's very easy to check this equality here. And we also get that it's, by exactly similar reasoning, it's also WB union B times W of B to the minus 1. So this set here is so here we've got the set of all words beginning with A to the minus 1, and this is now all words we get by pre-multiplying each of those words by A. That always cancels off the A to the minus 1 at the start, and we get the rest of the word, so to speak. And it's actually easy to check that in these cases, once again, these are disjoint unions, but that's not so important. What's important is that this is A1 union A, A2, and this is B1 union B, B2. So we have indeed shifted these sets and these sets by elements of the group so that the unions of the shifted things give us back the whole of the set we started with, the whole of A2. So this indeed establishes the paradoxicality of F2. Okay, so that's the end of step 3. Now we're still not looking at anything like the unit ball. So how are we going to go to the unit ball? And that's what we do next. So step 4 is the paradoxicality of the two-sphere. So I'm going to write like this, boldface S2. This is the surface of the unit ball. So S2 is, remember, so it's all x, y, z in 3 space, such that x squared plus y squared plus z squared equals 1. So now we're getting into the serious geometry of the situation. And we're going to do that by making a jump from the free group on 2 generators to S2. And that depends on the following lemma. And again, I'm not going to prove this, and this requires quite a technical proof. It's one that involves sort of real calculation, and it's that there is a group embedding from the free group on 2 generators into the group SO3. Well, let me remind you that SO3 is the group of 3-dimensional rotations around the origin. Let me write 0 underline for the origin. That's the 0, 0, 0 point in 3 space. So a very, very famous group. So I'm just going to say the proof is fiddly. That's a little bit complicated to do. You can find it online if you're interested in looking for such things. So Maybe before going on, just say it's not actually too surprising though, because the group of rotations is very rich, and if you take an irrational rotation in one direction and an irrational rotation in some orthogonal direction, maybe it's best to make it actually at an irrational angle rather than than strictly orthogonal. But if you take irrational rotations using different irrational factors in two different directions, then it's really not so surprising that you have a group that that if you consider all combinations of those two rotations, that gives an embedding from the free group into the group of rotations. Because you're essentially saying if you have a non-reduced word here, you can never form the identity element. And that's because you're combining lots of irrational rotations going in different directions, and it's not surprising that doing that you can't ever get back the identity element. Right, I've said, I think, enough about that. So what we want to do now is use this fact to transfer the paradoxicality of F2 to the paradoxicality of the sphere. So let's let G be the subgroup of SO3 corresponding the subgroup given by the image of the embedding of F2 in SO3. Well, let's not put the of there, the embedding. So remember the rotation group, SO3, of course, its canonical group action, very famous group action, is to consider its action on the two-sphere, because that's the primary thing, geometric object that one wants to rotate in three-dimensional space, the surface of the unit ball. That's the two-sphere. So since G is a subgroup of SO3, it also acts on the two-sphere. So we have an action of G on the two-sphere. Inherited from the action of SO3 of the group of rotations. Now, as you probably know, and you can almost certainly visualize even if you don't know it, whenever you have a rotation of the sphere, it has two fixed points, because any rotation has an axis, and the rotation shifts every point on the sphere, so it properly moves every point on the sphere apart from the place where the axis intersects the surface of the sphere. So for example, and the rotation of the Earth, which is nearly a sphere, the two fixed points are the North Pole and the South Pole. But anyway, every rotation has two fixed points. So for every G in G, the action that maps a 3-vector to G acting on X, the rotation of G on X, has two fixed points. Because this action is a rotation. Let's point at the arrow. So this is just some property that generally holds of rotations. So I'm going to identify the set of all these fixed points. So let D be the subset of S2, be the set of all these fixed points. But it's a countable set. Of all these fixed points. Why is it countable? Well, that's because G itself is countable. So G is the image of F2. F2 is the free group on two generators. Its elements are reduced words. They're only over a finite alphabet. There are only countably many reduced words over a finite alphabet. So note well, NB, G is countable. Right, so we've got a countable set of these fixed points, D. We're going to see why we need that in a moment. But because these are fixed points, if we remove them from S2 and we consider the action of the group G on, well, if we consider what the elements of the group G do under the action to the set S2 minus D, because these were fixed points, it turns out that if you're not a fixed point, then the group will never move you to a fixed point, because if it did, then the points would not be fixed by the group. So importantly, G also acts on the set S2 where we've removed this countable set of fixed points. Okay, now this might seem rather technical, a bit mysterious where we're going. Hopefully that is going to become a little bit clearer in just a moment. So before doing that, let's proceed by now taking the next step. And this is one that I want to highlight because we're now finally getting to the place that we're going to use the axiom of choice. You might have completely forgotten by now that this is a lecture on applications of choice. Well, here finally we only need to use it once, and here is the place we do it. So let K be a set be a subset of S2 minus D containing exactly one element from each orbit of G. So the group acting on this set is moving elements around. It gives us an equivalence relation. Two elements are related in the equivalence relation if there is some group element that takes one element to the other. And so the equivalence classes of this equivalence relation are called the orbits of a group action. And it's just the same kind of application of the axiom of choice we saw before, that we are extracting exactly one element from each equivalence class. So here, maybe we put it in red. We use AC. Okay, and now, given this nice set K that we've chosen, we can show a lemma that the set S2 minus D is G paradoxical. Hence, if it's G paradoxical, well, SO3 has more elements in the group. Hence, it's easier to be SO3 paradoxical than to be G paradoxical. So it's also SO3 paradoxical. And the proof now, we're going to see why we had all this fuss with fixed points, because we've got S2 minus D, and it's actually easy to see now that that this set is K together with words starting with A acting on K. So I'm referring to elements of G using we've got an embedding of F2, so I'm just using the word for the corresponding element of F2. So the point is the sphere with this countable, with a set of fixed points removed, we can again partition it in the same way that we partitioned F2, just by applying the elements in the W set, the words beginning with B, for example, to all elements of the set K. And because K only contains one element of each orbit, whenever we apply elements to the group to elements of K, we'll get something else in the same orbit. Well, anyway, I'll comment on that in a moment. So let's finish the line. So the point I want to make is that this is the whole of the group, because not the whole of the group, but the whole of the sphere with these fixed points removed, because any element will be in orbit with exactly one element of K. Then there will be exactly one element of the group G that will take us from the element in K to the element of the sphere that's not a fixed point that we were looking at, and that tells us that tells us which, depending on whether that element is the empty word or is a word beginning with A or a word beginning with A to the -1, that tells us in which of these sets it lies. But importantly, this union is disjoint because we excluded the fixed points. If we had fixed points in, then fixed points would occur in all the sets. So we would not have a disjoint union. So let me comment on that. The union is disjoint because we excluded the fixed points. And once again, we're going to take this to be A1, this to be A2, this to be B1, and this to be B2, and it's now the same proof before. So we have that S, the sphere without these fixed points of these countably many rotations. This is WAK union A times WA to the minus 1 of K, and it's also WB K union B of WB to the minus 1 of K. So this shows that it is indeed paradoxical. Okay, so we've nearly got that the sphere is paradoxical. The only problem is we've got the sphere minus these awkward fixed points that we couldn't quite put into the argument, but we now have another lemma, which is for any countable subset, of the sphere, we have that the subset, the sphere is, that should not be equal, but is equidecomposable with the sphere with that countable subset removed. So of course we're going to apply this to, in the case that D is the set of fixed points, but actually it applies to any countable subset. So the proof here, we've got a countable set of points, so because there are continuum many rotations, it's possible to find a rotation so now we're using rotations that are no longer in the group G that was our image of the free group on two generators, but instead we find a rotation such that D, the image of D under the rotation, the image of D under the rotation applied twice, are all disjoint. So we've got countably many sets and they are all pairwise disjoint. And given this, I think I can squeeze it into the, so then I can squeeze it into the last line here. So then the sphere is, we can write it as D star, where D star is the union of all these sets. So this is a countable set. If we rotate it, it's still a countable set. So we've got, if we rotate it again, they're all disjoint, but we've got countably many countable sets. So we're unioning them. We get back a countable set. Okay, there's a kind of another application of choice in that statement, but actually you don't need choice in this particular case to prove that. At least I don't believe you do. Anyway, if you find that a cryptic remark, don't worry about it. So of course, we can partition S2 like this, but the point is this is equidecomposable under SO3 with, well, we simply rotate D star and we keep this part unchanged. And this is the same as S2 minus D. Where D star is D union the rotation of D union the rotation squared of D union ... So the point is that here we're showing the equidecomposability by we've divided the sphere into two parts. This countable set of our countable that's generated from our countable set by rotating it any number of times, and it's easy to transform that onto the set where we miss out D because we simply rotate this once and we rotate it off D. So D gets to rho of D, rho D goes to rho squared of D, rho squared D goes to rho cubed of D. So we stay within D. So rotating this takes us to D star with the set D taken away. And of course, if we rotate this, then, well, we don't rotate this, we just leave this set the same, unchanged. Okay, so now we've nearly completed step 4, which is the paradoxicality of the two-sphere, because we've seen that S2, that the two-sphere with this, the countable set of fixed points taken away is G paradoxical, but also that it's equidecomposable. I just realised I need to correct this to this is equidecomposable in SO3. We've got that the sphere with the fixed points taken away is SO3 paradoxical, but with the fixed points taken away, that's equidecomposable with the sphere. So by our lemma from earlier, the corollary that we can transfer paradoxicality along equidecomposability. So the corollary is now that S2, the sphere, is SO3 paradoxical. So with this result, we already have a nice already a very strange geometric result that's not exactly the full Banach-Tarski theorem because it's not about the closed ball, but it's nonetheless saying that if we've got the surface of the sphere, it says we can partition the surface of the sphere into finitely many A pieces and finitely many B pieces, such that the A pieces can all be rotated to fit together to form the surface of the whole sphere again, and the B pieces can all be rotated together to also form the surface of the whole sphere. So this is already a very strange geometrical statement here. But anyway, having got this far, we might as well proceed and get all the way to the proof of the Banach-Tarski theorem. So now we're in step 5, which is the last step, which is finally paradoxicality of B, namely the unit ball, i.e. that is the B Banach-Tarski theorem. So, the first lemma, we're going to get so close. The ball, if we take the origin out of it, is paradoxical under the group of rotations. Hence, also under the group of proper rigid transformations, because that group contains all rotations. The proof of this is it's not hard from the sphere being paradoxical, because each point of the sphere, to each point of the sphere, we just identify to that point the ray, or the radius, if you like, that there's the straight line that goes from the origin to the point on the sphere. We miss the origin itself from that, but we consider the ray coming out that doesn't contain the origin but contains every other point on the straight line going from the origin until it hits the surface of the sphere. So basically we take our paradoxical decomposition of the sphere and we extend it to a paradoxical decomposition of the ball without the origin by attaching to each point on the surface of the sphere the ray going through the ball to the origin. So I'm just going to say follows straightforwardly from the paradoxicality, the SO3 paradoxicality of the sphere. And so then the missing thing we need to do is we need to now see that. So we've got that the ball without the origin is SE3 paradoxical. We just want to put the origin back in. So for that, it's enough to show that the ball without the origin is SE3 decomposable, is SE3 decomposable with the whole ball itself. And for this, it's a little bit similar to what we did to add the fixed points back in to the surface of the sphere. That may be slightly more fiddly. So let's do this anyway, because it's the last thing we're going to do. So let rho be an irrational rotation around the axis a half y 0. So we've got z is 0, x is a half, and we're allowing y to change. So it's like the y-axis, but it's shifted to the right along the x-axis by a value of a half. So we're going to rotate around that axis. Irrational means it's an irrational multiple of pi. So it's like a 180 degrees rotation. That's a pi rotation. That would count as a rational rotation. So with an irrational rotation, if you repeat it any number of times, you'll never get back to, you'll never get the identity. That's the point of irrational rotations. And so we're rotating rather than around the center of the ball, we're rotating around the y-axis, but positioning it at x equals a half, so that's sort of halfway between the center of the ball and the surface of the ball. And the whole point of doing this is in doing this, we are going to rotate the origin within the ball and get a sort of accountable orbit of the origin, that it'll go, each rotation will take it to a new position in the ball and we'll never get back to where we started. So I'll just note that rho is an element of SE3, so it's a proper rigid transformation, but not of SO3 because it's not a rotation around the origin. So the point of the irrational rotation is that the origin, then when we rotate it, and we rotate it again, and so on, they're all distinct elements of B. We stay within B because our center of rotation is at x equals a half, and we start off at the origin, so we stay within a circle. So we stay within, our origin stays within a circle that goes between the origin and the surface of the sphere. So we're going to define Z star to be the countable set of all rotations of the origin by some finite number of applications of rho. And then we have, so we need to show that B is equidecomposable with B with the origin removed, but we can write B as a disjoint union of Z star together with, of course, B with Z star removed. So it's going to be very similar to the argument we did with the fixed points. And once again, we simply apply the rotation to Z star. So we see that that's SE3 interdecomposable with, we apply rho to Z star, and we don't do anything to the other points in the sphere. And this is B minus the origin. Okay, so now, again, by the lemma that we can transfer paradoxicality along equidecomposability. So we have corollary of these two, that B is SE3 paradox. Sorry, there should be subscript 3, SE3 paradoxical. That is the VT theorem, Banach-Tarski theorem holds. And we're done, and it took quite a lot of time and quite a lot of work, and I hope by thinking through this, if you got this far, I'm sure not many people did, but congratulations to those of you who have got this far. Hopefully you've got some idea of what the pieces and the decomposition look like. That first you need to understand the decomposition of the sphere, and the pieces there are really quite awkward to understand because of this set K that we defined using the axiom of choice. But once we've got that, then the other ingredients, like this countable set of fixed points and how we rotate it, and then extending the pieces through the rays to go from the surface of the sphere to the rays in the ball that together fill the whole ball, apart from omitting the origin, and then the last bit with rotating the origin to deal with that. So all these ingredients all combine, and you can see that all the pieces that are used are rather peculiar shapes, not at all the sort of shape that is related to the kind of shapes one deals with in ordinary geometry. That's why I said maybe the area of the Banach-Tarski theorem is really somehow set theoretic geometry or something like that. It is a kind of geometry of three-dimensional space, but the kind of geometric pieces that we're using are very strange ones. Anyway, it's a somewhat unsettling theorem. It's the sort of theorem that one can spend many evenings pondering over what it means and what the correct way of dealing with it is, and whether really the axiom of choice is the right axiom for mathematics after all. But anyway, we have gone on for more than long enough. Of course, this was a rather technical proof. So, as I say, congratulations for everyone that's got this far. I don't really hold it against anybody if they didn't. And there's no lecture next week, as I've already said, so I wish you all a pleasant end of April and beginning of May holiday, and look forward to being back in touch in early May. So bye for now.